Yes.
Oh, thanks. Hello, everyone. I'm Yibo Zhang from University of New Hampshire, and my topic today is how to build a comprehensive magnetic database and the application to this database. So, how to discover a new magnetic material? This is very important, and we have several methods. First, use the experimental method. This method requires a lot of resources, which means it can be very expensive, and it takes a very long time to finish the experiment. And at the same time, you need to be very knowledgeable to plan an experiment, and you need to be lucky, and you need to have some intuition to succeed. In a word, it's not efficient if you do it alone. The second way is to do the computational method, like the DFT calculation. Well, they can be faster than the experimental method, but also the computational cost is very high. It's also time consuming, and because of these two reasons, it is limited to a small unit cell. It cannot be applied to something very large. And the most important thing is that it is less accurate. And the third method is data-driven method. And this is what we care about. It's because, firstly, it's very cheap. And if you have a model, you can predict anything instantly, which means it's very fast. However, like the data-driven method name defined, it needs a lot of data, high quality data and high volume data. So let's talk about data-driven. So for the data-driven method, the core is an algorithm, a model. So we use a machine learning model because it can learn from the data. It can learn by forming some pattern. And after you have the pattern, you can put something new to the pattern, and the pattern will give you the answer. And specifically for the discovering new material process, we will define two kind of model. The first is classification model, which will tell what's the type of material you care about. For example, it can tell you if this is a non-magnetic material or ferromagnetic material or anti-ferromagnetic material. The next step is regression model. This model can predict a specific property like the cure temperature. And here's an example to demo the workflow. So firstly, we have an unknown material, and the material will be transferred to the classification model. And for example, this is a ferromagnetic material, and it gives the answer. And then we give the material with relevant regression model, like the cure temperature, magnetization, cohesivity, so that we can predict this material with all the property we care about. Yeah, this is the data-driven method. And even though we already know the method is very simple, just to build some model, there's something. However, we need data. Data is the key point in the whole process. And there are some data sets. First is the computational data set. The DFT calculation is everywhere. We can directly use that. However, as the DFT calculation is not accurate enough, if we train model based on the DFT calculation, our model can be as good as DFT. However, it cannot be as good as experimental result. Another option is some experimental data. This kind of data set do exist. However, they have some problem. First, some of the data set is very small, and some of the data set quantity is not very good. The quantity is not good means that I found some of the data in the data set say there's a material. It is a ferromagnetic material. However, they also give that material with a new temperature, which is impossible. And the feature is insufficient, which means that we want every dimension of a material. For example, this is not a good example, but it have the material name, have the cure temperature. But if we train a model based on this kind of data, it's hard to learn because we only have the material name. We need something like structure to identify the material. And we can only predict the cure temperature because they only have this feature. So this is not a good example. We need to build something with high volume and much feature. So this data do exist actually, but they are stored in the publication. And there are so much valuable experimental data. However, can we manually extract the data? The answer is no, because we want to read a huge amount of a paper. That's impossible. And we found that the publisher like Aswell provide a very nice API, which can provide a bunch of a paper instantly. However, this format, the paper we download by this method is XML, which is not very clean, and it has a lot of unnecessary tags, but also have some necessary tags. So we need to remove the redundant one. And we build a workflow. We call it GPT article extractor. As you can see in the name GPT, we use a large language model. And in the whole process of the workflow, we firstly clean the paper, clean the XML format to a human readable format. And we assign the large language model with a role like a research assistant. And we give the model some task like, can you help me to extract the material compound from the paper? Help me to extract space group? Help me to extract the structure, etc. And we put the cleaned article with the prompt to the large language model, and it can give us the result. Looks like this. And we scan the whole elsewhere. We get a lot of data like this. We name our dataset the Northeast Material Database, NMAD. We have more than 26,000 of data in our dataset by reading through around 50,000 papers from elsewhere. And we have some overview of our dataset, like the category pie chart, like the element distribution, the new temperature distribution, and the current temperature distribution and new temperature distribution. And the most important thing is that we can see that the precision is very high, because we do not trust the database at the very beginning. And the large language model always output some thing that is wrong. So we randomly choose 200 data from our dataset, and we read the original paper one by one, and we extract the information by ourselves, and we compare the human extracted information and the model extracted information, and we found that the precision is very high. You can find that the magnetic property is not very good. It's a little bit lower. It's because many magnetic property are stored in figure. For example, the coercivity, and they do not show in the text. And our workflow is based on text. So for image, we cannot cover right now. And this is all the feature in our database. There's too much, but let me split them to 3 parts for you. The last one, the brown one, is some supplementary detail, DOI, which can help you to refer the original paper. Experimental is you to tell the difference between the experimental data and the theoretical calculation, because the experimental data is more valuable. And the first part, X, is everything about the materials itself, like the composition, like the crystal structure, that is parameter space group. And the Y is everything about the magnetic property, like the current temperature, new temperature, coercivity, etc. And we have the database. And the next step is to build a model so that we can map the material information to the magnetic property. Then let's talk about model. The first model we built is classification model. We use the random forest, and this is the result to validate the precision. And we use 2 different datasets. For each of them, the y-axis is actual value, the x-axis is the predicted value, and the result located in the diagonal means the prediction is perfect. And you can find that most of the prediction are in this line. So this is good. We also build a regression model. So we choose the Curie temperature to predict. But we can predict any things. So we built 3 different models to predict the Curie temperature, the random forest as well. Ensemble neural network, which is a combination of a different neural network, and XGBoost, which is similar to the random forest. And same thing for the y-axis. This is the predict value. For the x-axis is the actual value. And the red diagonal means that the predict and the actual value are exactly the same. And any dot around the diagonal means the prediction accuracy is very high. And we have the R-square and the error. So we have everything right now. We have the data. We build the data, build model based on the data. And next, we want to find some high performance magnetic material. We firstly download a lot of data from the material project, and we use our classification model to filter out the ferromagnetic material. And we use a regression model to apply the filtered list. Then we generate a table like this. So for this one, each of the regression model predict a very high Curie temperature. Specifically, every prediction is higher than 500 Kelvin. The next step, we need to validate, and this is the future work. So let me recap. We have 3 results. First is GPT article extractor. It can generate database automatically. It is scalable, and it can be extended to other fields, not necessarily to magnetic field, but also maybe superconductor or some other things. And the NIMAT, this is a database. This is very large, and the quality is very high. And also you can download it online. The third work is we build some model. The model can help us to find new material with high performance. And because our data is so valuable and we want it to be published to the community and everyone can access the dataset instantly. So we built a dataset. We built a platform which called nimat.org. If you are interested, you can scan the QR code as well. So through this platform, you can download our dataset directly. You can search the elements that you are interested in just by click the element in the periodic table. You will get a list of relevant material, and we plan to expand the dataset as well. And we will implement more function, like we will implement our pre-trained model to this website so that everyone can see if the material they care about have a good performance without training their own model, without code anything. Yeah, so that's it. Thanks.
Thank you very much, Yibo, for the very nice talk. So the floor is now open for one quick question.
Yeah.
A question about the oh, there was a last hand. Okay, sorry.
Okay, I also have a question. For example,
Yeah.
in some articles, it is really common to see the same alloys being published with different properties. So I think it's common for me to see the same alloy with different TCs documented for literature. Do you take into account that while you are doing your data sets, or you utilize, for example, papers that are highly cited, so it is more probable of being the right set of parameters?
Excuse me, I don't fully understand your question.
So you are taking some properties from the articles, right? For example, the TC.
Yeah.
But
Yeah.
for example, there are several articles with the same alloy, but being documented with different TCs.
Oh, yeah. Yeah, you are right. So basically we just collect the material and the structure. If the structure are different, it's okay. But if they are same, everything is same, just TC is different. When we train the model, we will use average value because basically the TC will not change too much if they are exactly same. Is that what your question?
Yeah. Thank you very much. And
Yeah.
again, thank you very much for your very nice talk.